My name, as was referred, is Nikoletta Vlachou, and my presentation concerns life cycle assessment methodology. I'm a member of the research unit of Advanced Composite Nanomaterials and Nanotechnology that is in the School of Chemical Engineering at the National Technical University of Athens, and it has been established since 2006. These are some of our achievements. We have over 70 papers in international journals since 2006, and we have participated on various projects, national and international. Now, my presentation will have this structure. First of all, I will refer to maritime industry and why it's so important. Then we move on to the coating systems for ships painting, and we'll discuss the environmental impact that they currently have. Then I'll try to introduce you to life cycle assessment methodology, and we will see a small case study that we'll have the opportunity to discuss the results that came of this study and every other question that may occur. First of all, as it is easily understood, the transportation sector is an important contributor among industrial activities, especially maritime transport versus the air and road transport is a relatively cleaner form of transportation per kilogram of transported material. However, due to the globalization of manufacturing processes and the growth of global scale trade, there is an increase of certain types of emissions that may cause severe impacts on human health, climate, and also ecosystems. So, the assessment of shipping emissions on the global and regional scale is of great interest. Those emissions that I mentioned can be classified to three categories. Those that are related to fuel consumption, and they are released during the operation of the ship. Secondly, the anti-fouling coatings, that they have many times water-soluble compounds that also released to the seawater. And last but not least, due to the maintenance and the waste that are produced during the maintenance of a ship. An integral part of all the organic solvents and diluents are the volatile organic compounds, or else VOCs, that are used in the paint formulations or during the application of the paints on the shipbuilding, and the reduction and the elimination of those and other toxic or carcinogenic components from traditional paint products has been attempted for many years. A very good example of this, of a toxic component, is tributyltin, or else TBT. That was the favorite biocide for use in anti-fouling paints since the late 80s, when a Europe-wide ban on the TBT was used on boats under 25 meters. This was due to the observance that TBT was causing severe damage to shellfish communities, and not only. Before the widespread use of TBT, copper was used as a biocide, but it does not have so good results, anti-fouling results, as TBT. However, this is the most effective alternative, as the TBT is banned now, among with other biocides that are currently used. However, all those anti-fouling coatings still have a detrimental impact on the ecosystem, and they need further research. The subsequent painting of ships during and after construction is a highly complex technology because each surface requires a unique treatment. However, it is hard to combine all the requirements in any surface within one paint, as it is easily understood. So the solutions may be some multi-coat systems, such as this one. In practice, the coating system of the ship's hulls consists of a layer of primer coating, such as epoxy primer, wash primer, coal tar epoxy, chlorinated rubber, as here, and so on. In the slides picture, some of the primer coatings can be that are currently used are depicted, epoxy and chlorinated rubber. And those coatings can also have some anti-corrosive pigments for anti-corrosive protection. The intermediate coating, that is called tie coat, and can be considered as a barrier for sealing or as coating that helps the adhesion to, for the top coat of the on the primer coat. The top coat is the anti-fouling paints. The coating can also offer, the intermediate coating, the tie coat, can also offer anti-corrosive protection. And the last layer, the top coat, the anti-fouling one, has a dual function. First of all, the anti-fouling protection, as it is easily understood. And the second one, the decrease of drag resistance. For the external surfaces of the simplest, however, comprises of an alkyd primer for the external surface of the ship and an alkyd enamel over it. Now we will move to the life cycle assessment. Some introduction to the methodology. We use this methodology for assessing the environmental aspects associated with a product over its life cycle from the beginning, as in this picture, from the resource extraction to design, manufacturing, distribution, use, collection, until the final stage that may be the reuse, the recycling, the energy recovery, or the disposal in some place. I want also to say that LCA is a standardized method by ISO 14040, and there are two important applications of LCA. The first is the analysis of the contribution of the life cycle stages to the overall environmental load. And the second one, it may be the comparison between products for internal or external communications. The concept of LCA started at the 1960s. Then the oil crisis came, and there was a need for development of LCA thinking. The interest increased in Europe till 90s, until today, where there is a wide international spread. Now, for conducting and life cycle assessment, there are a lot of impact assessment methods. An example of them is the RECIPE method, the Eco Indicator 91, and the CML-IA. The RECIPE method that we used, due to its impact categories that are more relevant to the marine environment, is the successor of the Eco Indicator 99 and CML-IA. Precisely, it integrates the problem-oriented approach of CML to the damage-oriented approach of Eco Indicator 99. But let me explain what is the problem-oriented approach and what is the damage-oriented approach. The problem-oriented approach defines the categories at the midpoint level with a relatively low rate of results uncertainty. However, this solution leads to many different impact categories, which makes extremely difficult to draw conclusions as the results are much more complex. On the other hand, the damage-oriented approach has only 3 impact categories, but with the increase of uncertainty. We have much more uncertainty. So the recipe came that combined these two. It has 18 midpoint impact categories. 10 of them are related to the marine environment, and we have 3 impact categories that we're going to see right now. The first impact categories at the endpoint level is the human health, expressed as the number of year life lost and the number of years lived disabled. The unit is years. The second one is ecosystems, expressed as the loss of species over a certain area during a certain time, and the unit is also years. The third one is resource surplus cost, expressed as the surplus cost of future resource production over an infinite time frame, considering a 3% discount rate, and the unit is $2,000 US. The midpoint categories, some of the midpoint categories that we used in our study are those that are depicted in this slide. Some examples are the human toxicity, the freshwater eutrophication, the freshwater ecotoxicity, and marine ecotoxicity. Our case study was referred to environmental impact of marine paints, and especially to the anti-fouling coatings. The goal was to evaluate the environmental impact of the water-soluble compounds that are released during the operation of a barge tanker. But why a barge tanker? We used this type of ship because it was already available in the database of the commercial software that we used, so it was much easier to begin with. The functional unit that we used is the one barge tanker with a total capacity of 1,002,000 kilograms. And its dimensions are shown in this table and also in the picture above. We used length overall 60 meters, the breadth mounted almost 16 meters, the depth 6 meters, the draft almost 5 meters, and I already mentioned about the dead weight. For simplification reasons, we used flat geometry in shape of a rectangle in order to calculate the appropriate quantity of the paint used to paint the ship, the barge tanker. The fuel consumption was excluded during our study. Every one of the water-soluble compounds of the coatings were released in seawater for the operating time period, and the weighting factors for the inventory analysis were not taken into account. We assume that the barge tanker operates for 2 years. That's why the maintenance and final disposal are excluded, and it was difficult to calculate the fuel consumption for such a short period. The port facilities, the canal in which the barge tanker transports, and the production stage of the used marine coatings are not taken into account. And energy consumption during production of the paints, their packaging, and their transportation to the shipyard are also excluded. We only wanted to see the environmental impact of the anti-fouling and the effect that the released compounds may have to the marine organisms. Okay, by entering now our data to the commercial software that we use, this tree diagram was automatically made, which depicts the interaction between the different materials used and their contribution to our final product. As it can be seen, for each of the coatings, resins and solvents are the main factors that are taken into account for the impact assessment, as the other compounds are added in very small quantities. So practically, we assume that they do not have such effects. And those are our endpoint results. As we can see from the red column, the anti-fouling paint has quite an impact to the 3 categories. human health, ecosystems, and resources. And then the alkyd paint have also a negative impact on ecosystems. And all the other components of the paint system that we use do not have such effect. For example, primer symbol, much fewer. The midpoint results are depicted with this diagram. As you can see, the impact categories are quite a few. The anti-fouling, again, we can see that has an effect to all the impact categories. Climate change, ozone depletion, human toxicity, even in metal depletion due to the copper that it contains. Also, we see that has a great impact in freshwater eutrophication, and this is due to the zinc phosphate of the anti-fouling coating. And we can see that alkyd paint again has an impact to ecotoxicity, ozone depletion, climate change. Those two are from the components of the coating that have the more negative effect to the ecosystem. The anti-fouling coating contributes to marine ecotoxicity. All the other coatings have lower impact, as I already mentioned. And anti-fouling contributes not only to the marine environment, but also has a negative effect on human health and on resources too. The alkyd coatings also exhibit higher impact on ecosystems due to the resins that used in their production, and the impact of the other two primers, the epoxy and chlorinated rubber, is lower as they do not contact seawater directly. Some future recommendations to continue are the need for replacing of the toxic compounds that are included in marine paints, and also the need for development of innovative coating systems with anti-fouling activity but with fewer bioaccumulative effects in higher organisms. These innovative coating systems may possibly alter the fuel consumption also. And as far as the LCA concerns, it is recommended to use the information developed in an LCA study as a part of a much more comprehensive decision process, or to understand the broad or general trade-offs. Also, we can compare different LCA studies only if the assumption and the context of each study are the same. And LCA may contribute to decision making, comparing different production routes and materials. And as we try to prove, it may also be contribute to maritime industry. In this time, I want to thank Maritime, a national project that funded this study, as well as my co-authors too. And thank you very much. This is the time for questions. I'm a chemical engineer, yes. Yes. Yes, well, well, the next step is to compare new anti-fouling coatings with other compounds that have replaced copper in the much we use anti-fouling systems with lower copper and other substances, other compounds, and we can compare the traditional ones with the innovative that we're going to make. Excuse me? Well, we have some early results, but they're part of a project that is still running, so they are quite confidential. Well, as I mentioned, it's quite difficult. It's quite difficult, and it's difficult because it's difficult to convince the paint industries not to put copper in the coatings that they make. But okay, as a part of a research, it's quite interesting.
It's a work also with the same project. We have tried to replace copper with some species like enzymes or with carbon tubes in order to improve also the surface of the coatings. These are quite confidential because but we have also tried to find how we can replace overall with other sites.
Have you ever looked into the total environmental footprint of copper versus the more fuel we burn?
I'm not sure I understand the question.
Ships with a dirty hull use more fuel, cause more pollution.
Yes.
Is it better to pollute the air with fuel or the water with copper?
You're not totally right, but it's quite difficult to obtain such data. Here I'm presenting you a study with a time frame of 2 years. It was difficult to find the data of fuel consumption. That's why I excluded from this study. But yes, as a future plan, it is also to make a